Good morning all of you for these presentations. As discussed in the last class, we talk about river stabilizations. Today I will discuss about the river stabilizations of part 2. And you know it, there are a lot of experience on how to stabilize the river bank throughout the world, most especially in the Brahmaputra basins or the alluvial rivers in our country, but elsewhere in the world like in river Mississippi, river Elo, there are a lot of experience, the field experience used to protect the river bank. So, mostly I am following it this part of the book as Riverbank Stabilizations with a series of case studies from different part of the world. Looking that if you look at today contents, we will again talk about how to design the riprap rebatement, which you can see it is very easy to dumping the stones on the river bank, but that is not the correct. We have to properly design the river rebatement, river bank rebatement protections work, which may be a stone riprafs. Okay. And nowadays we also talk about the river health. So, that is the reasons the new approach of natural way to protect the river bank by planting the vegetations. That the concept also is going on, and he is also improve the river health. We also very briefly will talk about in presentation forms what it happens, the history of the river bank protections works in Brahmaputra rivers and small rivers like Brahmini rivers. Then we will talk about the windrows, trenches, Gabion matrices and the retaining walls, which a part of the geotechnical engineering. So, here I will go contextually that what we need to do as a river bank protections work, but most oftenly we do not encourage to have a retaining walls for a bigger river, big rivers like Brahmaputra rivers and all, but very site specific we can have a retaining walls. Let us go for the next slides, which is the repeating the slides of the last class. If you know the design velocity, okay. So, most of the times we can find out what could be the design velocity, that from the design flawed our experience running the HackerS models, we can know it what could be the maximum velocity or that the velocity, the extreme velocity we can consider the design velocity. So, if I look at this curve really design chart, if you look at it is a very clear cut, it is a velocity versus the diameters, the equivalent spherical stone diameters and the stone weight, and you have a different degree of the slopes, okay, different degree of the bank slopes. So, we can find out, for example, if I am considered to design velocity 4 and I have a 2:1 and that is the representative the size of the stones which is coming as closer to 0.5 meter. That is what the D50 or representative diameters, but we can have the gradations. So, look at this design chart prepared by US crop of armies, which gives us a very interesting figures that if I know the design velocity, I can compute what will be the equivalent or D50 or D representative value for to obtaining the riprap size. Also we follow the guidelines, the what should be the gradations and what should be the packing of these materials. Looking that part, let us go for the next part, which is very easy part, is that we talk about the filters. So, when you do stone riprap or the Gabion matrix, okay, you can have a stone riprap and Gabion matrix. Just below of that you should have the finer materials. Below of that you should have a geotextiles. If you look at that the geotextile materials are there, which acts like a filter between base and revetment, the riprap zones. Okay. So, there is a base materials and these filters act like prevent, it should be fine enough to prevent the base materials from escaping through the filters, that is what is the idea, but it should allow the water can seeps from these filters comes out, that is what it will take care of as we have a groundwater, as you have the increasing the level of the rivers and the groundwater table fluctuations will be there and the water fluctuations can seep through these, but not the base material. That is the reasons it should be fine enough to prevent the base material from escaping through the filters, and it must be more permeable than the base material. So, water can seep through that. The gravel filter or synthetic geosynthetic cloth filters nowadays commonly we use. So, like that the basically the revetment it allow water to drain it and it should have a stability and permeability, the properties for better filter materials. Now, if you look at the next slides which we talk about what should be the filters, that is what the US Army crops of engineers guideline, okay, design guidelines. What they had said it should have a size of gravel in the filter blanket should be from 3 by 16 5 mm to a upper limit, maximum size approximately 90 mm. The filter thickness should not be less than 20 centimeters. The filters are 1/2 of the thickness of the riprap is quite satisfactory, plus it should satisfy these 3 conditions. Okay. The ratio between the D50 of filter by D50 of the base should have a lesser than the 40. The ratio between D15 filter, D15 by base should range between 5 to 40 and D15 by D85 filter and the base should be the less than 5. So, if you look at that, as we know what could be the base materials, that is the base already you can geotechnically test it, what is the base material particle size distribution curve. From that we can find out D50, D15 and D85, and based on these criteria we can find it what should be D50 for filter, D15 for filters, and these 2 criteria we have to hold it, which will be allowed to have a proper drainage, proper water escaping from the base to the through the filters to the out from the base. That is the criteria, and from the design guideline from US Army Corps of Engineers, they decide this design criteria. That is what we should use it to know it what should be the and many of the times also we follow multiple layers instead of single layers filters. And if you look at that part where you have, and it can have a synthetic filter cloths or geosynthetic materials nowadays so often use it, which will be the consist of plastic cloth and woven plastic material or geosynthetic materials nowadays so oftenly used to put it these ones. And if you look at these figures, we should have the gradations. Okay. If you look at that, if the bigger material smaller than that, D1. So, D1 is increasing D2, D3 and D4. So, we can have put the coarser to finer and finer grade. So, that is what is there, and this is what is your base materials, or you can put a geotextile filters in between that to avoid these gradations from coarser to finers. We can have a geosynthetic filters. So, there are the design guidelines are there how to use geosynthetic materials, what should be the property of geosynthetic materials which provide as a protective blanket for the sand and gravel on the filters. The sides and the two of the filter fabric must be sealed it. Okay. The trench so that the base material does not leach out around the filter cloth. The care also should take in joining adjacent section the soft filter fiber together. So, it can have a monolithic to stitching these geosynthetic geotextile materials. So, that is geotextile filters we have been using it, but we need to do a proper geotechnical design to know it how we develop such a way that this base material does not leach out around the filter cloth. Also the joining adjacent sections the soft filter fabric together. So, we should take care of that. So, you can see that how geosynthetic materials as a filter cloths we use for as a filter materials for revetment and the base soil. As we designed the revetment with a filter and base compactions and changing the slope of the bank, we also should know it what type of failure can happen it, what type of riprap failures can happen. Like it can have a particle erosions. Okay. That means, if I have a as you put these stones, okay, so it can erode the particles wise one by one, as you see that type of erosions can happen is, or it can sliding it, you can see it these figures. So, as a block all this riprap material can slide it, or it can slump it, or it can have a slide slope failures. Many of the times we have this type of failures. If you look at the revetment, you will have a either riprap slump will be there or side slope failure is there. If you do not design the riprap accurately properly, or you cannot do the layout of the riprap effectively, then you can have a side slope failures, we can have a riprap slump or the particle erosions and the slides. That is what nowadays we try to avoid it, because we follow a Gaussian matrix concept. That is what I will show to you. Nowadays we follow this Gaussian matrix concept. So, this type of particles erosions or the slides does not happen it, but it can happen the riprap slumping or the slide slope failures. And if you look at that, if this groundwater tables are fluctuating more, you can have a saturated zone, and that the slope failures can happen it. So, you can have a geotechnical study more details about the bank materials and the hydraulic characteristics. If you know that very well, then you can avoid the side slope failures of the revetment structures. That is the point. And if you look at that, again just to have today that the particle erosions is a most common erosion mechanisms, but we try to avoid nowadays, because you have Gaussian matrix concept. That is what the individual stones are removed by the impact, the steep bank side and riprap gradation, that is too uniform. As that the riprap should have the gradations, it should not be the uniform size. That is what we discussed in the last class. The same things, if you look at that, the riprap gradations is, if it is too uniform, you can have a particle erosions. Same concept is that if you look at these sliding failures, which is a downslope mass movement of the stones, it happens like that, and this slide usually initiated by channel bed degradations. What it happens is that if the channel bed is this like and it is degraded, okay. So, it's if it's erosions are happening it, okay, the deepening of the channels are happening it can have the channel bed degradations happening which undermines the two of the riprap blanket, then you can have this type of slide. The presence of filter blanket may provide a potential failure plan for the translation side. So, thus you try to understand it. If you have your filter blankets, and which can also a failure plan for the sliding on that. Cause of that steep bank slide, so presence of excess hydrostatic pore pressures, loss of the material at the two of riprap blankets. Okay, we just try to understand it, how the structures fails it, if you have a degradations and if you have a excess hydrostatic pore pressures is developed in the bank soils and steep bank side slope. Basically, when you protect the bank, we do the slope reductions, we cannot put it in a steep banks. So, if you look at next one, which is riprap slump, that way we can understand it that side slope failure is a rotational and the gravitational failure movement of materials. That is what it happens, it is concave upward curve. The causes slump failure is related to the shear failure of underlying base materials. Basically, it is giving about a geotechnical where the failure part excesses pore pressures in the base of materials and steep side slope. Now, if you look at that, to avoid these failures, what we do it? We always have a tie back. Okay. So, we extend it, the matrix, the given matrix or the riprap matrix inside the bank, which act like a tie back. Okay. Also, when you do a launching apron, if you look at thickness is a T, we put it additional height is 2.5 times of the T. Okay. That is what initially we put it that once. As the river scours happens, this materials goes down it and falls in like this. So, we have to take care of, because of the scouring mechanism, because of river degradation mechanisms, the river bank protections what we have done it, that should take care of the scour formations. That is the reasons if you look at, if a launching apron we provide it, which will have a thickness T is here, on the bank, on the bed we put it a thickness which is 2.5 times of the T, and after the expected scour, these materials can again have a fall like this. So, similar way if you look at the plan forms, how you do the revetment. So, if you have a river going like this, you can see this, you should protect the river bank in this side, because there will be point bar formations and also this side. But if you look at, there should be overlap zone, there should be tie back, this should be designed properly. The tie back should be there, the overlap should be there, and the protections of both the outer bank should be put in such a way that it should not have a failure mechanism will happen it, because of if you protect it partly, it is not a successful story. So, we have to protect the river as a single entity, as the river curvatures are there, we should have the revetment in both the sides, we should have a tie breaks and we should have the overlap. Lot of design guidelines are there, what should be the overlap, how to make the tie back, or you can have a more detailed geotechnical and the hydraulic experiment, the laboratory experiment to find out what should be the dimensions of this plan form of these revetment structures. So, if you visit any of the river bank, you can see these revetment structures where you have a bank erosion is quite dominated. Next points what we are talking about, when you look at these launching aprons, you should have a very much knowledge about the scouring mechanisms. Okay, how much of scour is going to happen it. Like this is a riprap apron which we provided, this is the water surface slope. So, we can see that there will be the failure things is changing it. So, okay, this failure surface is changing it because of the scouring regions. So, the scour you have to anticipate it, what could be the scour happen it because of these river protections work and hydrodynamic force and the river curvatures. That way you can find out what could be the failure surface will happen it, and based on that we should have the protection mechanisms. The launching aprons is a flexible aprons, can be laid horizontally on the bed and foot of the revetment. So, this is the launching apron is what you will, it will be flexible, and the scour occurs on the material will settle it over the side of the scour hole on a natural slope. That is what we plan it. So, that is what we should anticipate it. If there is a scour holes, the launching apron should be very flexible, so that the launching apron the materials can cover up on the scour hole holes, and the scour zones can be protected naturally by the river dynamics. You can settle down it. That is the reasons it needs to have a lot of experience in the river levels. We design something, some river revetment work, implement the river revetment work, monitor the river revetment work to try to know it, what should be the criteria follow for launching apron, so that the river bank can protect it during the extreme scour formations formation stage. That is a quite challenging work. It is not a just dumping the stone on the river bank. That is my point to tell it. It is not a just a dumping the stone on the river bank, then eventually that what will be failed. We should have a proper designing of the river revetment work. If you look at that, what the experience, the river stabilization work is not very easy task. When you talk about river like Brahmaputra, it is a so large dimensions, we cannot think it the river bank protections are a simple job. So, if you look at that, if you look at these figures, you can understand it what could be the height of the bank. Okay. The height of the bank is a 6 feet tall person is standing here, and you can understand with this scale which could be more than 30 feet. That is what is above the free surface. Okay. There could be below another maybe 30 feet. Okay. So, if you look at this river bank, okay, so gangetic, okay, so high river bank of 60 feet. Okay. And if you look at the river erodible bank materials which are close to the sand and the silt, okay, they does not have or some clay compositions. And if you look at the river bank protections, which is a porcupine structures, which is just standing over that and which is falling down it. Okay. And you can see that how erosion processes are happening it very dynamically, instantly it is eroding the toe materials, collapsing these bank materials, and at the top the river bank protection is standing it, trees are standing it. So, if you look at that, the bank erosion process what it happens in Brahmaputra rivers in the scale that does not happen in many part of the world. So, we should try to understand what type of bank erosion process are happening it. And we have a small structures like a porcupines. If you look at these concrete structures, the basic idea for these concrete structures is to reduce the velocity. Okay. If I reduce the velocities, that is what can start the sedimentations depositions. Okay. The siltations will start it, and that siltations can facilitate the river to divert from that locations. So, this type of smaller structures we have been putting in river bank of Brahmaputra rivers just to have expected that the velocity near the bank is going to decrease it, and as it is going to decrease it, it can initiate the sediment depositions, and because of these sediment depositions, as we expected it, river can change its course. Okay. It can go from the locations where it is. Okay. But some success stories and failure stories are there, but this is what the riverbank protections for this alluvial river like this, where the bank erosions are really, it is a quite challenging process what it happens it. Some of the cases we can have a protect the rivers with a soil cement, a compositions of soil and cement bag, you can see it, and the top you can have a protections work, but that is what also can be possible where you have not these compositions, or you want to protect where you do not have a much secondary current is there, you can think it to protect the river bank with a soil cement and with a some sort of gabion or this surface protection systems, like putting the some stones or even the bricks to protect these ones. So, if you look at that implementations what is going on, the same way if you look at this is what I explaining it, the huge Prokopine structures, okay, that is what is called Prokopine fields, and this is what, because of these Prokopine structures, it may be facilitating depositions. Okay. If you can see that Prokopine structures and this the depositions, and because of that river might have changed its course from these protections to other part. So, these are the structures what is implement is it is a simple tetrahedral structures and it is quite stable, and those are structures we use it just to protect which are the vulnerable reefs. Success and failure stories are there, and I am not going to discuss much detail on that, but this is what the basic idea when you do it. But if you look at this river bank protections in Brahmani rivers, okay, where it is a smaller rivers as compared to the Brahmaputra, and you can see this rivers band, you can see the embankment, you can see this floodplain cultivations. So, as we have been discussing, the same concept is there is a floodplain, there is an embankment. So, we have enough floodplain, we have given it to rivers, and it has the agriculture activities within the floodplain, and that is what is there. Okay. And the cases where you have a river band, okay, the channel band is there in Brahmani, and you can see these spore structures, okay, from even from Google data. You can see this river spore structures which is facilitating the river to go like this, okay, not to attacking this bank. So, you can see this a series of spore structures, are there which is divert these flow streamlines away from the bank. That is, you can see it, and there are earlier there used to have a weir structures to protect the maximum flow or protect the maintain the navigable flow depth. Okay. So, if you look at that way, our success stories for the smaller rivers is quite impressive, but bigger river like Brahmaputra and partly Ganges are not that successful, because the dimension of the problems are, as we have been discussing, it's still it's a complex task to protect the river bank in Brahmaputra, where you have a so dynamic processes are happening. This is the concept many of the peoples in the worldwide, they are talking about river health. The basic idea is that to bring the river as close to natural conditions, that means any rivers you can have protect with a vegetations, okay, protect with natural vegetations, and because of this protection of the natural vegetations, what is going to happen is that the velocity reduces. as we increase the roughness, Manning's roughness coefficient, putting these vegetations, what is happens is velocity reductions happens, okay, which is facilitated for the sedimentations, which we need it during the high flood periods if there is a sedimentations, and that what will facilitate also the growth of the vegetations. So, we try to look at how we can reintroduce the vegetations on the river banks and its potential floodplain area, so that we can improve this, increase this Manning's roughness coefficient, which we can know it because of increase of Manning's roughness coefficient, velocity reductions will be there, and which can facilitate the sedimentations. And not only that, near boundary, near bed, okay, and the bank, the flow structures will change it, flow and sediment structures will change it, which is quite complex that way. So, if you try to understand it, that is what is there, and if you look at that the examples which is there, that if you have a river bank like this and if you put the vegetations, and you can see that how it is a very natural vegetations can have a effectiveness in terms of protecting the bank, but be remember it may happen for the smaller rivers where that significant order of flow is not there or the velocity is not there. So, smaller rivers we can protect naturally with help of the vegetations, changing the near bed and bank flow and sediment structures, changing the flow resistance and changing the velocity, that is what would facilitate it and vegetations grow it. So, this is what basically environment conditions, which is, as I said, that it will improve the river ecosystems, root system may increase the overall bank stabilities, reduce the flow velocity, induce the depositions. That is what I explained it. Okay. And there is limitations, there is a failure of vegetation subject to undermining, may not have withstand alternative period of wetting drying periods, uprooted by freezing, thawing of ice, suffer wildlife, livestock damage. Okay. It is just expected. If you grow the vegetations, it may not effective for all the cases. Okay. It can effective for certain range of the flow, the velocities and all, but if you have a extreme flood event, it may not sustain that way, or whether these vegetations remain grow throughout the years, taking care of wetting and drying of different durations. Now, if you look at next part, which is very interesting, that what type of vegetations we can put it. Okay. If you a river bank, if you look it like this is the flow, but there is a zone you will have the flow where you have the flow which is called the high stress zone, which is inundated throughout the most of the years. Okay. That is what this is a low flow, this normal flow. So, this part of the vegetation which is the splash zone, okay, where we can have a throughout the year you can have the waters. In that case you can have a semi aquatic plants, you can have a roses, sage, hibiscus. Okay. So, this is the area, so often the water will spreading it there, and there you can put the some vegetations will be semi aquatic plants. Okay. If you have a bank zone which is above the normal to the high water levels, this is the bank zone which is above the normal high water levels. It is inundated at least a 60 days durations once in every 2 to 3 years. Okay. Inundation does not happen so often here, it is inundation at least a 60 days durations, that you can have a hibiscus or weedy plants, we can put it that. If you terracing zone, okay, beyond that you have a terracing zone. Okay. you have a splash zone and you have a bank zone, which is usually not subject to the erosive actions, less often flooded, native grasses, herbs, shrubs and trees can be planted it. Most oftenly I will concentrate it in natural for river systems mostly follows like this, okay. Whether we can facilitate to have a same natural conditions by artificially planting these trees, native grasses, weedy plants or semi-aquatic plants. So, basic idea as a river engineering is that we try to improve the river health, okay, as well as we can protect the bank protections, okay, because we change the near bed or near bank hydraulic conditions. That is we try to understand it, but how effective it is, all are the big questions marks when you talk about extreme flood conditions. That's where to be look at more technically how effective it is, but there are the cases we have been advocating to have a ecosystem based river protections work, which can be implemented for the smaller rivers where we are not we have modified the river ecosystems. So, those regions we can plan it to have a different type of vegetations like a splash zone, bank zone, terraces zone, we can put the different vegetation and we can make it river ecosystem as closer to the natural conditions, and by the way we can improve the river health and also we can protect the river bank. Let us look at river bank protections. What we look at very traditional way to protect the river bank like windrow or the trench. If you look at these figures, okay, it is a very simple way. You just dump those stones on the river bank or you create a trench and fill up the stones. What is our idea is that as the river eroded, okay, as it is widening the channels, this stone materials will fall down it. After that it will be naturally have a protections. It create a natural formations of river blankets, okay. Bank blanket you will create it, it is naturally. So, that is what is the windrows, just you dump the stones of different sizes and you just wait to river to erode that part. As it is erode this part and it is fall it during the natural conditions and it will create a blanket of river protections work, it is naturally by river dynamic forces. But this is what nowadays we are not practicing it because it is quite expensive. And we do not know whether river can come to that locations or not. And it is same way we can have the trench facility to have a protections of the bank, and or you can have a launching approach. So, you can have a launching these materials from the top and you can go like this, okay. So, we can have windrow revetments is piling a sufficient supply of erosion resistance material on the existing land surface along the river bank. That is what is earlier we used to do it. Similar to windrows, but material is buried here, the same concept. We also depend upon the size of the stone, well graded stones, and we also talk about the relative thickness of the final revetment, the stone diameters, greater the velocity, steeper the side slopes. Okay. Basically, this is the practice used to do from the Brahmaputra Ganges rivers in Bangladesh, and they have been very old practice to do this type of river bank protections using windrow or the trench concept to protect these things. But nowadays we cannot do those type of bank material, we cannot put it huge, and we cannot wait for the river to erode it and have the protections, but we go for the launching way and proper river bank protections work. Now, if you look at sacks and blocks, which most often use it. One is that you can have a 1 by 1 like this. Okay, when you have the side slope ratios like this, or you have a 1 over 1 by 1, this stacking will be there, or you can have a stacking like this. Then you have a 2 protections and the scour depth, and after the scour the filling materials. So, if you look at these ones, which in generally if you go to any of riverbank protections, you can see that depending upon the slope, you can stack it, the stack and blocks. Okay, that's what is that, and most probably you have to look at what you have been doing it. Okay, protecting the river bank. Most of the nowadays we talk about the Gaussian matrix, because as you know it, the individual stone, if you put it, there could be a particle erosions, there could be a chance to have a slidings. To avoid that, we last few decades is introduced the concept of the Gaussian boxes. You can see that there could be a box with a length and height, and you can fill up the stone here. Okay, and box with a wear mass. So, if you have a box with a wear mass, so you can put these stones, and those stones can have a particle level stability, as well as it can act like a mattress. So, if you look at this, act like a mattress. So, that is the more stable will come it when you combine the riprap stones with a Gaussian boxes. Okay, with a Gaussian boxes, and if you tie off all these Gaussian boxes, it can act like a matrix. It is a big matrix. Okay, we can put a stone Gaussian matrix on the river bank, which is much more strength as compared to the individual stones. Okay, so that's the reasons nowadays we have been using this concept of Gaussian matrix on river bank protections, where we need to protect it, because the cost is quite effectiveness in terms of reduction of the thickness of the stone, rebatement, and as well as it creates a monolithic structures. Okay, it create a monolithic structures, single structures, so that any sort of the failure mechanisms can be prevented because of Gaussian matrix. So, basically it is a broad baskets tied together by side to form a continuous blanket of protection is placed on smoothly graded river bank slope. So, we have to first smooth it river bank, or you make a reduction of the side slope. On the reduction of the side slope, you can lay out Gaussian matrix, and as the Gaussian matrix is simple things, it is a boxes with a wire frameworks. So, you can have a from like a baskets, you can put the stones, it can be tied down it side by sides, and can have a place on a river bank. Okay, that's nowadays the technology. And if you look at that part, we have designed for similar conditions for the Brahmaputra rivers. Okay, and if you look at this is a plan form. Okay, this is the what is jetty locations. We try to design the protection of the jetty with the Brahmaputra rivers. The design velocity is about 5 meter per second. The scouring depth as it goes beyond the 30 meters. Okay. So, we try to protect these things, that is what we design it. River bank protections work for Brahmaputra rivers, and you can see this plan view for design velocity, and you can see there is a apron here, the stepped apron you put it, and there is a tie concept is there, and there are different length is there, and if you look at this covering stepwise apron, we have been propagating it. So, just follow this all and this is a Gaussian matrix what we have designed it, and more detail I am not discussing it. but these things partly is implemented in many part of the Brahmaputra rivers protecting the banks, but it is a bit expensive as compared to the others. Now, if you look at which is this technology is bit costly, because is articulate concrete mattress can be put it, okay, as it will be a concrete mattress, okay, which I believe it can be okay for the smaller rivers, and in the urban areas we can think it to have a the cable connected, and you have a concrete mattress, and you can put it this apron area after the showers. Being it's flexible, it can come to the stage and you can have an anchoring concept. So, the basically this type of protections work we do it, it is quite expensive for a urban area where the land cost is too high. To protect the urban area, we can have a articulate concrete mattress, just like that what we talk about the Gabion mattress. So, similar way you can have a concrete mattress, okay, and you have a arrangement of cable and the rods, you have a steel cable anchoring, scour protections after the scour, all you have to, the design concept is same, but we have changed the materials. Is a articulate concrete materials, is a precast concrete blocks held together by steel rods and cables. Basic unit can be commit to be 1.3 meters, 7.6 meters and 7.5 thickness. It is flexible, strong, and in complete coverage of the river banks when properly place it, but it is too much expensive, and you need to look at what type of protections you will do the land mass, okay, which regions you are putting it. But as I said it, in case of the urban area, we can think about have a precast concrete block, which is advantage for us, because we can do the constructions of these river bank protections very fast, because precast concrete blocks are there and we can just join it and protect the river bank with having this allowance for the scouring zones, and proper anchoring should be there, and should be the flexibles and should place over the filter materials. That should be the conditions as we discussed in the previous slides. There are concept as I showed it, there could be a soil cement, okay. You can have a riprap, it's quite alternative, but unusual way of what you do it a soil cement. Soil should be easily polarized and contain at least 5%, not more than 35% silt and clay, okay. We just mix the soil with the cements, okay, with some percentage of the cement, and soil cement can be placed and compacted on the slope as steep as 2 horizontal, 1 verticals. The placement of soil cement in horizontal layers could be 2 to 3 meter wide, 15 centimeter thick, okay. So, this is what showing it, but what I am to tell it, this soil cement concept more detail you can get it from, but it can be used for a smaller rivers where we do not have to put a lot of we do not have to put more expensive river bank protection work, and we can take a risk for the river bank failures, and we can improve the soil cement. The basically we are increasing the critical stresses, okay. Just we are increasing the critical stresses, okay, because of soil compositions, and that critical, that is the reasons there will be no erosions will happen it, and that way we can protect it. That is the basic idea here. You improve the critical shear stress by combination of the soil, cement, and that will give us a soil cement blocks which will have a higher the critical shear stress, and because of higher the critical shear stress for erosions, and that is what is the it's protect the banks. That is what the it protects the bank. Now, if you look at I think we will be discussing more about the retaining wall in the next class, and with this let me concluding these lectures, and this is my research groups who have been helping me to develop this course. But before this, if you look at that, people talking about a concept is called a roadmap for a healthy Ganga. Okay. So, if you try to understand it, river protections work, we should look it in terms of river health, not in terms of just protecting the river bank. So, with that concept we should move it, and with this let me conclude this lecture. Thank you.